Hello learners, I am Dr. Subodh Kisharwani working with Indira Gandhi National Open University in School of Management Studies. The topic which I am going to talk today is probability under statistical independence. Prior to going into the depth of this topic, I just want to throw a light that this is part of our course called MCO3, Research Methodology and Statistical Analysis, and we are in Unit 13, Block 4, which emphasize more on the testing. And if you go into the backdrop, you will find out that we have got a chapter called probability distribution, hypothesis of testing of hypothesis, and testing of hypothesis 2. So prior to going into the detail of this topic, I just want to throw a light that we have already covered the probability in length. The preamble part of probability, we have covered the rules of probability, and now we are emphasizing more on probability under statistical independence. And if you go as far as the syllabi is concerned, as far as the table of content of this particular chapter is concerned, we have already covered the fundamental concepts and approaches to probability rules, and as far as the probability rule is concerned, we have covered additional rule for multiple exclusive events, additional rule for non-mutually exclusive events, and now we are focusing on probability under statistical independence. And after that, we are going to talk more about probability under statistical dependence and then Bayes theorem. So without much emphasizing on the other aspect, we just concentrate on the particular theme which we are talking today, that is the probability under statistical independence. And if we talk more about this presentation, it introduced quite a few new concepts. Again, joint probabilities, marginal probabilities, and subsequently also conditional probabilities and independence between events or random variables. So anyway, independence is a fundamental notion in probability theory as in statistics and the theory of stochastic process. Two events are independent, statistically independent, or stochastically independent if the occurrence of one does not affect the probability of occurrence of the other. So what is the difference between probability and prediction that need to be focused? Understanding the difference between a prediction and the probability of a particular outcome occurring is an important distinction for successful investors. Predictions are absolute, right or wrong. Probabilities run a spectrum from highly unlikely to extremely likely. So there is a lot of overlapping when we talk about probability and statistics. Probability starts with a population, often described by a probability distribution, and predicts what will happen in a sample from that of population. So we have seen that the probability distribution is very important aspect which we are going to cover in our forthcoming session, and it is going to talk more about the various things which comes under the probability distribution. So statistics starts with a sample of data and describes the data informatively or makes inferences about the population from which the sample was drawn. So this module concentrates on the inferential rather than descriptive side of statistics. So in probability there is a very important distinction. In probability, there is a very important distinction between the words and or, and means the outcome has to satisfy both conditions at the same time, or means the outcome has to satisfy one condition or the other condition or both at the same time. So this is a very important difference between the probability, and there is a logical definition of independent events. Since we are emphasizing more on independent events, and as far as the dependent events are concerned, which we are going to take in our forthcoming session, but in this particular session we are focusing more on independent events. So we will begin with a logical definition of independent events. The first thing to note is to throw away any definition you may have of the word independent or independence in the English language. You must base what you understand about our definition of independent events only on what we have to say about it. In English, we often think of independent as being separate, not overlapping. However, we already have a definition for that, which is disjoint events. So in probability, disjoint events are events that do not overlap, that cannot occur at the same time. The probability definition of independent event is a statement about the equality of probabilities. So if we talk more about statistical independence, two events are statistically independent if the probability of any one of them is unaffected by the occurrence of the other. Independence can ordinarily be assumed from the nature of the random experiment, for instance involving separate tosses of two fair coins, a dime and a quarter is there. So if you see a difference between independence and dependence, so statistical independence, no association, statistical dependence, association. So if you talk about statistical independence, like population conditional distribution on one variable, the same for all categories of the other variable. And if you talk more about statistical dependence, which emphasize more on the association, conditional distributions are not all identical. So example of statistical independence is like if you take a table of income above, average below, and happiness very pretty not to. So if as far as the income is concerned, happiness is 32%, very happiness is 32%, it's in common to all, and prettiness is 55% in all, and not to is 13% to all. So this is a way of doing the thing. So when are things, now the question is that when are the things independent? So is gender independent of profession? I think most police or fire brigade personnel are men, most kindergarten teachers are women. So, is the probability of having a PAN card independent of profession? Are rickshaw pullers likely to have PAN cards? Is the probability of defective product independent of factory where it is produced? Old plants, worn out machinery like to cause more defects. So these are the things where you will find out that a lot of independency is there. So statistical independence, if you are going to talk about, for example, if a fair coin is tossed once and supposed head comes, then this event has no effect in any way on the outcome of second toss of that same coin. Similarly, the results obtained by drawing hearts from a pack has no effect in any way on the result obtained by throwing a dice. These events thus are being termed as a statistically independent events. Now we can take some good examples which can defend this particular terminology in a more polished manner. Two events are independent if knowing one events occur does not change the probability of the other event. Now if we take example 1, if I roll a dice twice and record the result for each toss, the fact that I rolled a 1 on the first toss does not change the probability of rolling a 1 on the second toss. The event A is equal to getting a 1 on the first toss and B equals to getting a 1 on the second toss are independent. Knowing that A happens does not change the probability of B. So that could be one of the example, and if you go through the second example which can give us the more clear picture, more appropriate for us. So is it what we draw two people from the entire population at random and ask them whether or not they have ever had a heart attack? If the first person say yes, this will not change the probability that the second person will say yes. These two events are independent. Now, prior to talking more about the preamble part of independency or the statistical independence, we are going to emphasize more on the types of probability under statistical independent case, which is going to be bifurcated in 3: marginal probability, joint probability, and conditional probability. If you talk about dependent case, this is also, talking in the same lines, that is marginal probability, joint probability, and conditional probability, but with a different mandate, with a different way of doing the thing. So once we are talking about that particular manner, we will emphasize more on that. So probabilities may be either marginal, joint, or conditional. Understanding their difference and how to manipulate among them is key to success in understanding the foundations of a statistics. So now, the first is marginal probability under statistical independence. Two events A and B are statistical independent if and only if their joint probability can be factorized into their marginal probabilities, that is PA intersection B is equal to PA into PB. So if two events A and B are statistically independent, then conditional probability equals the marginal probability, and PA by B equals to PA and PB by A equals to PB. That is probability of A upon B equals to probability of A, and probability of B upon A equals to probability of B. So marginal probability under statistical independence is the probability of the occurrence of an event. And if we talk more about the term called marginal probability, the probability of an event occurring, probability A, it may be thought of as an unconditional probability. It is not conditioned on another event. For example, the probability that a card drawn is red, then probability of red is 0.5. Another example, the probability that a card drawn is a 4, and probability of 4 is 1 by 13. So this is how the marginal probability is going to be explained. And now after talking more about the marginal probability, we are jumping on the joint probability under statistical independence. This is also termed as a multiplication rule of probability. So on the other hand, apart from the joint probability, it is also known as multiplication rule of probability. In many situations, we are interested in finding out the probability of two or more events either occurring together or in quick succession to each other. For this purpose, the concept of joint probability is used. This joint probability of two or more statistical independent events occurring together is determined by the product of their marginal probability. So if we talk about the joint probability or the marginal probability, it is denoted as P A and B, and the probability of event A and event B occurring. So it is the probability of the intersection of two or more events. The probability of the intersection of A and B may be written as P A intersection B. And for example, the probability that a card is 400, then probability of 400 could be 2 by 52, 1 by 26. So there are two red 4s in deck of 52, the 4 hearts and the 4 of diamonds. So if you talk more about the multiplication law for independence event, just to remind you that for independent events, one outcome is not dependent to occurrence of the next outcome. The second basic law is multiplication law of probability is intended for computing joint probabilities. So probability of A and B equals to probability of A multiplied by probability of B. So the multiplication law of independence event is need to be illustrated. Suppose a perfectly balanced coin is fairly tossed twice in succession, then head 1, tail 1, head 2, tail 2 are the events, and probability of two heads is the probability of the joint event of head 1 and head 2. And if we denote in terms of probability of head 1 and probability of 2, head 2 equals to probability of head 1 multiplied by probability of head 2, which comes to 1 by 2 multiplied by 1 by 2 equals to 1 by 4. So there are a lot of examples which we can take and different. I think we have talked in terms of statements and in terms of the mathematical probability tools. So among 24 invoices, if we are going to prepare by a billing department, 4 contain errors while the others do not. So if we randomly check 2 of these invoices, what are the probabilities that both will contain errors? Neither will contain an error. So the probability of getting an error on the first draw is 4 by 24. As we pick only 2 invoices and want to have error in both invoices, so after the first pick with error, we have only 23 invoices left, and among those 23 invoices, only 3 invoices could have errors. So the probability of the second event picking an invoice with error in second draw is 3 by 23. The probability that both will contain error is 4 by 24 multiplied by 3 by 23 equals to 1 by 46. So it is coming 0.0217. So the probability that neither will contain error is 20 divided by 24 multiplied by 19 by 23 and comes to 95 by 138, which is giving a value of 0.688. So the general multiplication rule, if you emphasize more, suppose that a quality control inspector has established that 10% of the electric assemblies fail the circuit test, 20% of the failing items have poor solder joints. This experience provides that the following particular assembly will fail and have poor solder joints. So probability of F is equal to 0.10, probability of P oblique F is 0.20, and the multiplication law gives joint probability that a particular assembly will fail and have solder joints. Its probability of F and P equals to probability of F and probability of P oblique F. So it is coming 0.1 into 0.2, which is coming 0.002. So this is called general multiplication law, and a lot of other examples are there. So probability of A and B is probability of A multiplied by probability of B and A, and probability of A and B is also equals to probability of B multiplied by probability of A upon B. So that we have to notice that the probability for the first event in the product is an unconditional one, whereas the second is a conditional probability for the other event given the first. Now, talking more about, joint and other thing, we are focusing on the conditional probability under statistical independence. And this third type of probability under the condition of statistical independence is the conditional probability. It is symbolically written as P A upon B, that is probability of A by B, the conditional probability of occurrence of event A on the condition that event B has already been occurred. In case of statistical independence, the conditional probability of any event is akin to its marginal probability when both the events are independent of each other. So suppose there are two events A and B with probabilities PA and PB respectively, and if we assume the probability of an event B is influenced by the outcome of event A, and we also know that event A has occurred, then the probability that event B will occur will no longer be probability B. So the probability of event B when it is known that event A has occurred is defined as a conditional probability and is denoted by P B by A and read as probability of B given A. So this is the way by which we are going to denote that PB by A is going to be denoted as probability of B given A. So the conditional probability PB by A and the conditional probability PA by B are respectively. So if you see the formula, probability of B given A equals to probability of A intersection B divided by P A, which is known as probability of A, and where probability of A is unequal to 0. And if we talk about probability A given B is equal to probability of A intersection B divided by probability of B, where probability of B unequal to 0 again, and where probability of A intersection B, also denoted by PAB, is known as the joint probability of events A and B, then gives rise to the following: PA intersection B equals to probability of B given A multiplied by probability of A by B multiplied by probability of B. So what we have observed that in probability theory, two random events A and B are conditionally independent given a third event C precisely if the occurrence of A and occurrence of B are independent events in their conditional probability distribution given C. In other words, A and B are conditionally independent given C if and only if given knowledge that C occurs, knowledge of whether A occurs provide no information on the likelihood of B occurring, and knowledge of whether B occurs provide no information on the likelihood of A occurring. The concept of conditional independence can be extended from random events to random variables and random vectors. Random variables we have already covered in our forthcoming session, which was more focusing on the probability distribution, and we will see that how random variables talk more about this particular aspect. So if you see this particular box, which is known as the colored box, each cell represents the possible outcomes. The event R, B and Y are represented by the areas shaded red, blue and yellow respectively. The overlap between the events R and B is shaded purple. The probability of these events are shaded areas with respect to the total area. In both examples, R and B are conditionally independent given Y, because probability of R intersection B given by Y equals to probability of R by Y multiplied by probability of B by Y, and but not conditional independent given not because probability of R intersection B not Y is unequal to probability of R not Y and probability of B not Y. So this is a way by which we are going to distinguish the colored boxes. And conditional probability under statistical independence is the probability of event A occurring given that B occurs. An example which we have taken in the past also, like given that you drew a red card, what's the probability that it is 4? So probability of 4 oblique red equals to 2 by 26 equals to 1 by 13. So out of 26 red cards, given a red card, there are 2 4s, so 2 by 26 equals to 1 by 13. So if we talk about conditional probability, consider how the probability value of one event is affected by the occurrence of another. A probability value computed under the assumption that the another event is going to occur is a conditional probability. So it may be possible to compute a conditional probability directly from known probability values using the following formula, that is probability of A given B equals to probability of A and B divided by probability of B. So it is more likely to rain tomorrow if there is a solid cloud cover than if there are patches of blue. So for the events rain and blue patches, the following value might apply, that is probability of rain oblique blue patches equals to 0.30. So the event rain is listed first and 0.30 is the conditional probability of the event. The condition given event solid overcast is listed second, and the vertical bar is a shorthand presentation for that given that. Should no stipulations have been regarding sky conditions, we might have probability of rain equals to 0.20, which is unconditional probability. So what we have observed that while talking more about the marginal, joint, conditional with respect to this independence statistical analysis, I think when we are going to summarize these three types of probability, their symbols and their mathematical formula, and under statistical independence is going to be emphasized or going to be placed with the help of this table, where probability type is marginal, then the symbol is probability of A, formula is probability A. If the probability is joint, then symbol is probability AB and the formula is probability of A multiplied by probability of B. And if we talk about conditional, then probability of B given A equals to the known as symbol and formula is probability of B. So now how to manipulate among joint, conditional, marginal probabilities, this need to be discussed. The equation below is means to manipulate among joint, conditional and marginal probabilities. As you can see in the equation, the conditional probability of A given B is equal to the joint probability of A and B divided by the marginal of B. So we can take another example which can talk more about that the conditional probability of 4 given a red card equals to 2 by 26 or 1 by 13, and this could be equivalent to the joint probability of a red and 4, that is 2 by 52 or 1 by 26 divided by the marginal probability red equals to 1 by 2, and lo and behold it works. So as 1 by 13 equals to 1 by 26 divided by 1 by 2, and for the diagnostic exam you should be able to manipulate among joint, marginal and conditional probabilities. So this is the way by which we are going to talk more about this particular thing, and in our coming sessions we are going to talk about statistical dependence with respect to this particular probability type. Either it could be the marginal, joint and conditional. So for this statistical dependence also we have this marginal, joint and conditional. So this is the way by which we are going to talk, and probability trees are useful to calculate probabilities, identify all simple events, visualize the relationship among the events, and probability trees are useful if it is possible to break down simple events into stages, identify mutual exclusive and exhaustive events at each stage, ascertain the probabilities of events at each stage. So if we talk more about it, a probability tree consists of some nodes and branches. Nodes, an initial unbound node called origin, other nodes each labeled with event represented by the node. So now we are going to conclude this particular term called statistical independence with respect to these three probability type. So independence is a fundamental notion in probability theory as in statistics and the theory of stochastic process. Two events are independent, statistically independent or stochastically independent if the occurrence of one does not affect the probability of occurrence of the other. Equivalent does not affect the odds. So similarly, two random variables which we are going to discuss in our forthcoming session under the ambit of probability distribution, we see that these random variables are independent if the realization of one does not affect the probability distribution of the other. So when dealing with collections of more than two events, a weak and strong notion of independence need to be distinguished. The events are called pairwise independence if any two events in the collection are independent of each other. While saying that the events are mutually independent or collectively independent, intuitively means that each event is independent of any combination of other events in the collection. A similar notion exists for collection of random variables. The name mutual independence, same as collective independence, seems the outcome of a pedagogical choice merely to distinguish the stronger notion from pairwise independence, which is a weaker notion. So in the advanced literature of probability theory, statistics and stochastic process, the stronger notion is simply named independence with no modifier. So the stronger, since independence implies pairwise independence but not the other way around. So anyway, I am going to wind up this particular thought which emphasize more on the statistical independence. In our coming sessions we are going to talk more about the statistical independence, and then we have another session which called the Bayes theorem, and then we are going to wind up this particular chapter and move to a next advanced the probability distribution. Thank you very much.